KG, will you be ready for tomorrow to review carbon 13?
Yeah, I'll be ready.
Okay, all right. Okay, so I hope you did look at the mechanism for this. You have a carbonyl compound. Remember, we are dealing only with aldehydes and ketones. And the reaction of a secondary amine with the carbonyl compound gives you what is called as an enamine. And this requires acidic conditions. Hope you've reviewed the lecture recordings from before. And this will ultimately give you remember there's a double bond there, enamine. It's like an ene and an ol. And it has two R groups. Okay. Can you tell me in the chat how many of you did the mechanism? One person did. Okay. So we looked at the previous one that shows the mechanism for the imine formation. Okay. So the mechanism is the same for the imine formation, they're saying, except for the last part, because we have a carbon-carbon double bond here. Okay. So those of you who did the mechanism will get extra points. I'm not going to show the mechanism here. You're still responsible for writing that out. And you have to look at the textbook to complete it, or your completed lecture notes. So the aldehyde or ketone will be converted to a carbonylamine, and then a few more steps will take it to the enamine. Okay, and like the other one, like the imine formation mechanism, start with acid attack, followed by acid attack, meaning proton transfer, followed by the nucleophilic attack with the secondary amine. With the secondary amine. I think we'll have a mechanism quiz over 19 before exam 3. So exam 3, part 1. just mechanisms. Part 2, reactions, spec, and others. Okay. So you're learning mechanisms on one day and then the rest of it on another day, and it's not overwhelming. Because you have quite a few mechanisms here, and you did have mechanisms for 18. Okay. All right, we'll talk more about dates tomorrow. So finish that mechanism. I request that you do. Now, summary of the two reactions. One with the primary amine and the other with the secondary amine. Okay. With the primary amine, you get an enamine. No, I'm sorry, imine. And look at the structure. Carbon, nitrogen, double bond is an imine. And look at the structure of the primary amine. You have R attached to an N, one R attached to the nitrogen. And so the nitrogen at the end must be attached to the one R. Now, the secondary amine, look at the structure. It has two R groups. So nitrogen at the end gets rid of all the hydrogens it has, but it cannot get rid of the R groups. So you cannot have a double bond here. You see that? You cannot have a double bond here and have two R groups. Nitrogen will have a positive charge. You see that? That's when you'll see in the mechanism, that's when it becomes an enamine. An ene has an alkene and then carbon nitrogen single bond. The mechanisms are very similar. You'll get something like that. That'll rearrange to give some like that. All right. So you have to know the mechanism. All right. Now, got that? Okay. Now, Wolff-Kishner reduction. So this is an application or an extension of what we just learned. Hydrazine. Okay, this is quite reactive. Hydrazine, common name, okay? So you have to know the name. This is like a primary amine attached to an R. Okay, it's like a primary amine attached to an R. Can you predict the product then? Can you predict the product? The product you will get is an imine. Can you draw the structure? The N must be attached to this group, whatever be it. There's a double bond. It's like a primary amine. This is your R group. Okay. See that? That's the imine that you get with hydrazine. And then you have a second reaction. The second reaction is like elimination. Here you have to know the reagents. I'm going to show the reagents here. Basic conditions and heat. Okay, that delta symbol means heat. And it gives you an alkane. Okay, looks like a miracle happening. And of course we have a mechanism, but nitrogen, you see, N and N, they become nitrogen gas. And these two steps put together is the Wolff-Kishner. It's a named reaction, which means it has the name of these people who came up with the mechanism. So you can start, look at the starting material. You can take the carbonyl and make it into an alkane. So overall, it's a reduction reaction. Overall, it's a reduction reaction. I'm going to put it all together for you. You don't have to know the mechanism for the second part. And know the structure for hydrazine. Of course, it has to be catalyzed by the acid, okay? H3O plus. First step. Now know how to predict products. Imine. Okay, but practice drawing all these. And then the second step is sort of like elimination. Now, if you have a gas or a solid formed in the reaction, if it's a reaction in equilibrium, as the gas escapes, the reaction keeps moving to form more products. So look at it overall. You take a ketone or an aldehyde. You can add this to your other reduction reactions. You will get alkane. Wolff-Kishner reduction. The next slide has the mechanism for the second step of the reaction. And you can look at it and see how the changes happen. Started off with the OH, proton transfer. So you have to get rid of the N2, see that? And then it escapes as gas. You don't have to know this mechanism, but you'd have to know the reagents used and the products formed. Okay. You don't have to know this mechanism in detail. You know, at the beginning, we talked about acidic conditions, basic conditions. If you have acidic conditions, the reaction species should either be neutral or have a +1 formal charge. Okay. Let's say you have Making this up. Okay, let's say you have this is for any mechanism, okay, or reaction. Let's say I'm doing this under acidic conditions. Okay, the tendency here is proton transfer. And also when you do your mechanism, remember, remember to show all the products. Even if you form water in a mechanism, you have to draw the product. It's either protonated or there could be some molecules that are like this, neutral. All right. What cannot be present? What cannot be present? Anybody can type in? You cannot have this. Not possible. You see that? There's acid there, so it will not let the oxygen have a negative charge. He'll go and protonate that, so he becomes neutral, and then protonate some more, so he becomes an oxonium ion. Okay, so you need to bear this in mind. Got it? Now we're going to look at the reverse of some of these mechanisms. Remember the acetyl has two R groups, plus water, H plus. This is the reverse. What does that mean? How did we form these? What is the other product? What did we use to make the acetyl? Aldehyde and ketones and what? Two molecules of ROH. Okay. This is called as hydrolysis because you're using water. Specifically, acid hydrolysis. Water, H3O plus. Now this will happen only under acidic conditions. If you try using the base, no reaction. Okay. Now we are going to look at one of these mechanisms. Now it's proton transfer is the first step. And of course you have an oxygen, right? One of those OR groups. I'm going to draw it again so you can see it better. By the way, I posted all the lecture notes as well over the weekend. I was able to go to campus. Everything that I write here, that got posted as well on campus. Can you do a proton transfer and do that first step? And all of these are in equilibrium as well, but you don't have to show that. Okay, any one of the oxygens, they get protonated. And then what happens here? Remember, we need to lose both the OR groups as ROH. Is the OR a good leaving group? Is the OR a good leaving group? No. Okay. So what have we done? We are making so protonation makes it a better leaving group. So what's the next step? What are we setting it for? Setting it up for loss of leaving group. Now, you can form a carbocation, all right? It can leave, form a carbocation, but looks like it doesn't allow it to form the carbocation. So this guy moves in, and this leaves. Okay. Okay, now it doesn't leave just like that. Remember, it's called hydrolysis. We've seen the acid part, acid catalyzed hydrolysis. So they're using water. So a nucleophilic attack happens. Nucleophilic attack happens. Now, can you show me how the nucleophilic attack will happen? And should the structure be cleaned up after that? Clean up structure. I'm just going to show that. You'd have to show all the curves. I'm going to make it look clean. And then H3O plus is formed. Okay, proton transfer. What does that look like to you? What does that look like to you? Jamie, what does that look like to you?
Hemiacetal.
Hemiacetal, very good. Okay. So you have to, in mechanisms like this, long-winded. So you have, remember when we formed the acetyl, we went through the formation of the hemiacetal. Now you're going back in reverse, you're rewinding. Okay, so acetyl to hemiacetal. Well, halfway through or more than halfway. Now we have to take the hemiacetal and convert that to the ketone. Okay, looking for paper, that's why I'm looking. Okay, so I'm going to take the hemiacetal. I'm drawing big so all of you can see it. Now you have to get rid of the other OR group. Okay, so what do? We do the acid hydrolysis again, or proton transfer, I should say. Okay, what did we do with the first OR group? You see, we protonated, right? So we are taking care of the next one here. You're making this into a better leaving group, and you have an OH there. Okay. Now you can ask, why not protonate that? Okay, that's why it's an equilibrium. This is going to be a slow step. There could be other side reactions. This is proton transfer followed by loss of leaving group. Okay, and you have to keep in mind here, you do not have any free carbocations formed. So you're going to lose this OR group, but this guy is going to come in. Now you're almost home. See that? Because this could have left and you could have had a positive charge there. And it may be formed, but it quickly shuttles between those two, okay, resonance. And then we don't need, the reaction is not with the carbon, the reaction is happening here, so they are only looking at that resonance structure. Now what do? Last one, home free. PT. We want to get our acid back. It's nice when, you know, we do it together. So it takes a lot of practice is what I'm trying to say. So you used at least 2 molecules of water in the mechanism. And I didn't keep up with this, but you get 2 ROH groups, okay, at the end. So here, you see, you would have had an ROH group here, okay? So don't forget when you do the mechanism. I wanted to use all the space to make it clear to you. All right. So acetyl converted to hemi and then to the aldehyde or ketone. All right. Good times, right? Now, We're not going to look at the mechanism here, but it's very similar. Is simply the reverse of the mechanisms of formation. Okay, so here, what do you call this? Amine. You should be able to recognize it. What is this? Amine. Remember, what did we use to make these? Carbonyl primary amine. Okay, amine goes with primary amine. Enamine goes with secondary amine. Again, note cards. So we don't have to go through the mechanism here, but it's like the acetyl hydrolysis. Got it? Primary amine, secondary enamine. We finished nitrogens. A quick look at sulfur, okay? So we are home free because we know about hydrogen nucleophiles. We've seen sodium borohydride and LAH. We've seen those mechanisms. Carbon, we've looked at Grignard. So we're almost there. Just one or two that are new work. Sulfur, so this is like ROH. Can you predict the product here? Think about what you get with 2 molecules of ROH. H plus. In parentheses, that means acid catalyzed proton transfer. How will you draw the product here? I can keep drawing it over and over again. Can you draw a similar structure here? And can you draw the cyclic version? Okay, so wherever you have sulfur, you put, wherever you have oxygen, you put sulfur. What do you call this? RSH thiol. Okay, thiol, like alcohol, this is thiol. And this is thioacetal. That's a common name. And this one would be cyclic thioacetal. Cyclic thioacetal. So it's very similar. Sulfur, similar to oxygen. Now, a couple of things that we could use this for. How did we get this cyclic thioacetal? How did we get that? use the dithiol, okay? And you get the cyclic thioacetyl. Now here's another reaction. Where you can take the aldehyde or ketone and you can reduce it. Okay, ultimately, it's a reduction. And here they use a special type of nickel. It's a catalyst. And you get an alkane. Okay, so you have Wolff-Kishner reduction, and then you have this, we'll call it the Raney-Nichols reduction. What do these do? Convert an aldehyde or a ketone to an alkane. Okay, so this is one method. And the other method is the Wolff-Kishner reduction. It's useful when you look at synthesis. So we finish up with sulfur nucleophiles. Next, we're going to do hydrogen, which is a review. So I'll ask you to go back and look at the mechanisms. The mechanisms from here, for the most part, are shorter, okay? Fewer steps than what you've seen. Got that? Okay. It's 12:50 right now, so a few more slides. Now, this is a complete review. We've seen how alcohols are reduced. Let me see if you remember everything. You get a few sheets of paper. So if you have a primary alcohol, what does it reduce to? I'm sorry, I'm asking the wrong question. It doesn't reduce any further. If you have an aldehyde, what does it reduce to? What does it reduce to? What is the product here? You studied this when you studied alcohols. What is the aldehyde reduced to? Jamie? Is anybody typing anything? What is the aldehyde reduced to?
Primary alcohol.
Primary alcohol. You have only one R group. See that? And this one would be secondary. So this is what we're going to see here. Now, what reducing agents will work for these two reductions? John, you have an answer?
What reducing agents will work? First one, isn't it like Na2CO207 with water and H2SO4?
Okay, that's the reverse of it, oxidation.
Oh yeah, you're right.
Yeah, that's for oxidation. I know that's a common mistake. So think about reducing agents. Hutch, you want to help him?
Would be NaBH4 and water,
Mhm.
and then LaH and water.
Yeah, LaH was with water. NaBH4, I don't think it needs water, but I see your point. Okay, good. Adela, you there?
Yeah.
Did you know the answer?
No.
No. You've forgotten? With LAH is very reactive, so you do the glove box or something like that, and then you remove it and react it with water. Okay, so you can use for both of these, you can use any one. I guess that's what you write here. Going back to the slide. This, by the way, is a ketone. NaBH4. Along with this, you can use an alcohol. So I think that's what Hutch meant. Okay. Now hydrides are strong. This is your reactive.
Dr. Mary,
Uh-huh.
with the MEOH though, wouldn't that make an ester? Wait,
No, you get MEOH as a product if you use an ester.
right.
Okay.
Okay,
This is one of the reagents used, like a solvent.
because it can be water, MEOH, or ETOH, right?
Yes.
Okay, now I remember.
Yeah. So that's what Hutch mentioned, that it's NaBH4 in water and or LAH in water. But with LAH, it's two different steps. Okay. And here with LAH, they can use a reagent that doesn't destroy this or the other reactants. But in the second step, we use water. Here, a polar solvent can be used with NaBH4. So this is your nucleophile. And these are strong nucleophiles. Supposedly strong bases as well. Okay. So if you use an acid here in this, it will react with the hydride and neutralize it. Okay. So that's why they use basic conditions. Something like MEOH promotes it, or ETOH can promote it as well. Okay. So we're not looking at the details of it. Just know that these are strong nucleophiles and no acidic conditions allowed. That's all we need to know for what they're doing here. So why they are stressing this for us is, what did we say? It's basic conditions. Your nucleophilic attack is the first step. Can you finish the mechanism? Okay. So here, if you had an acid, that would have protonated it and it would have reacted with the LAH also. Okay, that's what they're talking about. And then you take it out, and the next step is proton transfer with water. And it's basic conditions, so you get OH minus along with the alcohol. That's why they say it's done under basic conditions. Now, you should be able to do the same thing with NaBH4. With La, you have lithium plus. Wherever there's a negative charge, you put the plus around it. Okay, you don't have to show the counter ion, but any other product formed must be shown in the mechanism. You see, I tagged the Li plus there. Counter ions. These mechanisms are short and sweet. Now, the thing about the attack here, you see with this example, this can attack, remember your carbonyl compound is planar. Okay? We looked at that at the beginning of this chapter. It's planar. So the nucleophile can attack from the top. It attacks at a 45-degree angle, okay? It lands like a plane, or it can go from the bottom as well. Why am I talking about that? So if you form if you have a an unsymmetrical ketone, then you have a chiral compound formed. And because the attack can be from the top and from the bottom, like SN1, you can have an R and an S. Okay. It happens with unsymmetrical ketones. Of course, you have to check to see if a chiral compound is formed. And if it is, then you have to draw the mixture. What kind of a mixture is this? Some mixture with your racemic. Very good. And you will get very close to 50-50. Okay, so those are our hydrogen nucleophiles. I think you would have liked this section. It's a good review. Okay, we review the alcohols part. We look at carbons, and we looked at those as well. Let me see if I have a better slide there. Let me use that. Can you predict the product? Carbon nucleophile. What is this reagent called?
Grignard.
Grignard reagent. Yes, very good. Can you all predict the product? First of all, this is a ketone. Ketone will produce what type of a product? What is the functional group of the product?
Alcohol.
Alcohol. Hutch, what type of an alcohol will you get?
You would get a tertiary alcohol because
Mhm,
the methyl group will attack.
mhm. Very good. Tertiary alcohol. Shelby, can you try this one?
You get a secondary alcohol.
Very good. So this is a regular aldehyde. Very good. I'm going to put ET. And you have a longer chain. Here again, okay, you can have stereoisomers. That looks like a chiral compound to me. So you can have stereoisomers. C-link. Make sure. this point. We're going to look at two easy mechanisms. We've already seen the one with the Grignard reagent. Remember again, basic conditions. We have strong neutrophils. No acid should be present, otherwise it will ruin the reaction. Okay, so this could be your CH3 or your ET. Okay. Can you do the steps? We've done this like numerous times before. One more time. We practice. Another R group. Okay. And then you bring the water in. And if it's a ketone, you'll always get a tertiary alcohol. Okay. Aldehyde is it? Secondary alcohol. Did I make a mistake somewhere? It should be an R. If you want primary, you have to use methanol, the simplest aldehyde. Okay, again, a review. Don't forget about chirality, because I can have 3 different R groups, 2 different R groups. Okay. We're going to look at another carbon compound. It behaves similar to the CH3 minus or the R minus in general. Not seen this before.
Definitely.
So we,
Are we going to be meeting past one every Monday from now on?
possibly. Do you have to go to work?
Well, I'm supposed to work at 1:30 on Monday, so if we are, I just need to let my manager know.
Yeah. So can you like block it for like next week alone?
Yeah.
Okay.
And also this Wednesday,
Uh-huh.
me and a couple other people in our class have anatomy, and we
Oh.
have an anatomy test at 1.
Oh, you have anatomy at 1?
We have our exam at 1.
Okay. So, do y'all want to start the quiz at 11:30? Or do you want to like watch the recordings later? Let me know tomorrow.
Okay, because I know it's me, Deanna, and Adele. I don't think anyone else is in the Monday, Wednesday, Friday anatomy.
Okay, okay. All right. I can start early. We can start our quiz at 11:30, and then you can leave, whenever after that.
Just a heads
So-
up.
Huh?
I have micro starting at 11, but I mean, like,
11.
if I have to miss like the last half, well, actually, I think we might have finished lectures, so it actually might be all right. But if we do, I could still leave early.
Mhm.
So if we take a quiz early, I might just be a tad bit late.
Okay, okay. So, so
I'm
10
okay with just
For
watching
Chem
the
2.
recording after-
Huh? Go ahead.
Class before Chem 2.
What did you all say?
I'm okay with watching the recordings when they're posted.
Okay, okay,
We don't have to make everyone take the quiz early.
okay. All right. So we'll plan on getting in about 11:50 or so we can start the quiz on time and we can keep up. Okay. If it's a problem, let me know, email me, and then we can talk tomorrow as well. I'm just asking for extra time for the lecture. So, because some of these mechanisms take forever and then we forget what we talked about the previous day. So that's why. Okay. And I plan not to go till 1:30, probably till 1:20 today. All right. Okay. All right, the other carbon compound that I talked about is this guy. That's the Lewis structure. And with the carbonyl compound, you form what is called as cyanohydrin. Remember? Bromohydrin, chlorohydrin. This is cyano. Cn minus is the cyanide ion, the poisonous salt. Now, this can be obtained from HCN. Now, HCN is an acid, right? Hydrocyanic acid. Is that a strong acid? No. So HCN is a weak acid. Okay, it's a weak acid. So with the little amount of Cn minus that you get from here, and therefore they're going to alter the method a little bit. But it's similar to adding using the Grignard reagent. See that? You have a Cn and an OH. And the common name for these types of compounds is the cyanohydrin. Now, because this is a weak acid, you do not have not enough concentration. So what do? They add a little bit of a base, catalytic amount. And what is the base? A small amount of potassium cyanide. I wouldn't want to do this experiment in the lab. Or sodium cyanide. Okay. So this is the catalyst. It's similar to the R to the Grignard reaction. And then what they do is the reaction is done in the presence of HCN, right? So that guy produces the protons. And your Cn minus is regenerated. So you just need a little bit at the beginning, and then it's formed in the reaction. Okay. It is reused. This is a neat little reaction. And this is some kind of a mechanism that happens in the centipede or something. I used to talk about it because that textbook will describe the reaction. I'll look it up. Or maybe it's in the textbook still. Okay. All right, a couple more minutes. Let's look at the reactions. Can you predict the products? OH. CN. Okay. Here again, you got to be aware of chiral compounds. What is the name of this? Benzaldehyde. Know the Lewis structure for Cn minus. Okay, Cn has a lone pair here, but this is the one that makes the ion negative, the lone pair on the carbon. Got it? Just like the Grignard reaction. This is our last slide. What is the purpose of this? Okay, why do we care about cyanohydrin? What they do is, once the cyanohydrin is formed, now they take that, we look at mechanisms of all of these, during regular semesters, but not this time. So I know you're thankful that we're not going through this. This is a reducing agent. So completely reduces the carbon and the nitrogen. So what happens? The double bonds. It's more like adding hydrogens. It's like an alkene. You see that? It's like an alkene being reduced. What would you do? R, add 2 hydrogens, add 2 hydrogens here. You see that? It's similar to this. Just soaking up the carbon-nitrogen triple bond with hydrogens. Next, this guy, this is very useful too for synthesis. This is called acid hydrolysis again. Something we have to remember, because this is going to make carboxylic acid. So we're going to learn about this in chapter 20. Many of the reactions that you've seen will be repeated. the nitrogen goes away. Carboxylic acid. Okay, we usually see that very often when we do synthesis. CN hydrolyzing to form the carboxylic acid. It doesn't touch anything else. You see the OH is not messed up for both the reduction and the hydrolysis. We have one more carbon nucleophile. And we'll just basically look at reactions. And then another reaction. So Wednesday I'll finish that. And I will start chapter 20. In the meantime, when we do quizzes, could you all use Adobe Scan or something like that instead of taking pictures? Adobe. This is free. It's a free app. But if you are doing it, if the quiz or the assignment is unloading as one file, I'm okay. I remember some of you took pictures, and for a quiz, it's okay. I get 2 pages, but for the Gen Chem exam, some had like 7 or 8, and I like to make hard copies and grade. So I went to school and I made hard copies, and it took a long time, and it was not clear. Okay, so use Adobe Scan, and if you have iPhones, I think it's called Genius Scan. So some of you, if you are not aware of these, I suggest that you do that. And if for some reason you have to take pictures, just take pictures of the pages alone. Sometimes I get the table and everything else, and it's color. And so when I have to go then and use Paint or something to crop it. So Adobe Scan has been working well. Anybody using Adobe Scan in the class? No, okay. But some others were fine. I think Jamie's was fine. Hutch's was fine. Hutch's too, and Deanna's as well. It was different. There were different files. I was able to see it very clearly, but when it comes to printing, I think I had to crop it. Okay.
Did you say mine was fine?
Is that Adele?
Hutch.
Hutch, yours and Deanna's. It has the same file extension, so it's able to pull it up fine on the screen. But when I go to print it, I had problems. So if you when you take the scan, if you can avoid the surrounding areas, that'll be good. It's just a suggestion, okay? If instead of like 9 of you, if I have to do, if 7 of you do it like as a single file, it just reduces the load and the color, the color printing charges, or the cost, I should say. Okay, it's just a suggestion. But Adobe Scan, I tried it today and it worked fine. And I have an Android phone, but I think it works for iPhones as well. Okay. So if you have any questions, or if you want to ask me particularly about yours, I'll be glad to. And I graded the first page of the quiz. Like I said, some of the common mistakes, do remember to show all your positive charges and your negative charges, all the arrows, all the products that are formed at the end. And then those are the, little mistakes that I saw. And again, I was trying to print everything too. So I just have one more question to grade. I'll grade that tonight, and I'll scan it back. I'll use Adobe Scan. I'll scan it back and send it to y'all. Okay. All right. Well, thank you for your patience and for staying a bit longer. Appreciate it. So I'll see y'all tomorrow at 12:30. Is that okay? Shelby, will that work?
Yeah, that's fine.
Okay, it's 12:30 to 1:30. Just come, KJ's review and my quick presentation, and then we'll talk about lab stuff. Okay. All right, guys. Take care. Stay safe. Be very, very, very careful. And I'll see you all tomorrow at 12:30. Bye. Okay, bye. I'll stop recording.